Hello everyone. Let us study what are digital filter banks and how these filter banks can be used to decompose a full band signal into subband signals. If you see in the diagram, Xn is the input signal. It is a full band signal. H0Z, H1Z, H2Z up to H of M-1Z, capital M-1Z. These filters are constitute a filter bank, what we call as the analysis filter bank. And the signals that we get out of these filters x0 n1, x1n, x2n up to x of m minus n, these signals are known as the subband signals. Now the name subband is very intuitive because we are filtering in different frequency bands. So the output of these filters will be in different frequency bands. A digital filter bank is a collection of filters with a common input. This is the common input and a common and a summed output. That we will see because the next part of the analysis filter bank is the synthesis filter bank, and the output of the synthesis filter bank will be a common and summed output of all the subband signals. Now, there are two types of filter banks. One is the analysis filter bank. The other is the synthesis filter bank. The analysis filter bank is used to decompose the input signal, as I have already explained, into a set of subband signals, with each occupying a portion of the frequency band. So these signals will occupy a certain portion of the full band of frequencies. Xn is a full band frequencies, right? H0Z. Now, the H0Z filter response, it can be a low pass filter response. The last filter HM-1, this can be a high pass filter response, and all the rest of the filters will be band pass filters, right? H0Z can be low pass filter, HM-1 can be high pass filter, and rest all are band pass filters. Now let us look at what is a synthesis filter bank. The synthesis filter bank is used to combine a set of subband signals. So these are the subband signals coming from the analysis filter bank. In between the analysis filter bank and the synthesis filter bank will be some kind of processing that will be done on the signal. The processing may involve quantization, coding, or compression. So these type of processing will be done on the output of the analysis filter bank, and x0 and x0 hat n up to xm-1 hat. These are subband signals, and these signals will be applied to the synthesis filter bank. Synthesis filter bank will actually sum these signals and will give a common output x of x hat n. And now the question is that whether we are able to, because if you see the input signal is xn and what we are summing here is x hat n. The goal here is to synthesize in such a way so that the perfect reconstruction of xn signal should take place. At least it should be as close as possible to the input signal xn, and it performs the dual operation to that of the analysis filter bank. It actually synthesizes the signal, whereas the analysis filter bank will be used to analyze the input signal, right? Okay. Now the question is, what could be the frequency responses of the analysis filters? Because we have these filters H0Z, H1Z up to HM-1Z. What should be the frequency responses of these filters? Now the frequency response can be in different categories. This is H0, this is H1, this is H2. This is an ideal filter response where there is a clear-cut separation between the frequency response of H0, H1 and H2. Non-overlapping spectral response. So this will be a non-overlapping spectral response. right? This is actually ideal uh, spectral response, and this is H0, H1. Marginally, they are overlapping with each other, right? If you see the third waveform, the H naught is H naught roll off the where it ends. There only the H1 starts. I mean, this is again non-overlapping, but this is not ideal because there is a certain roll off the going from passband to the stop band. There is a transition width, so it will not be an ideal response, rather it will be non-overlapping response. Whereas in the second curve, the response is marginally overlapping. And if you see the third figure, if you see the last figure, then the response of H0, H1, or they are overlapping with each other. Now, non-overlapping spectral response is better as there will be no aliasing. When the two spectra of H0 and H1 respectively they overlap with each other, that will lead to aliasing. So non-overlapping spectral response is better as there will be no aliasing. But you have to design digital filters with very sharp roll-off and which may lead to drastic increase in the filter orders. Now the question is that if there is no overlapping between the response of H0, H1 and between H1 and H2, there has to be a clear-cut roll-off of the H1 and H2. There should not be any overlap. That means you will have to design high sensitivity filters, and that may demand actually the filter orders to be very high. Only higher filter orders can give us the frequency response like this. But the question is that if we can tolerate certain amount of aliasing and bring overlapping frequency response, the requirement of the filter orders will reduce. The complexity of the implementation of the filters will reduce, right? So non-overlapping response gives us a steeper frequency transition bandwidth slope. Filter order here in this case could be prohibitive because you will have to have a larger filter order. Whereas in the case of overlap, but of course you do away with the problem of aliasing. But in the case of overlapping, transition bandwidth slope is relaxed, but aliasing will be there. That means with smaller order filters, you can design the filter bank, and whereas there will be some kind of overlapping, right? That will lead to aliasing. So you have to actually make a trade-off while designing the filter. Okay, now let us look at how to design the digital filter banks, including the analysis and the synthesis filters, so that the ultimate goal is to reduce the error due to aliasing. A simple technique will be outlined for this class of digital filters, where we will start with the causal low pass digital filter, the starting low pass filter, which is H0Z, and it is assumed to be an IIR filter, and its real impulse response is given by H0N, such that H0Z is given by H0M Z to the power minus N, where N goes from minus infinity to infinity, right? Now, these are the characteristics of this filter. The passband edge and the stopband edge are around pi by m, where m is some arbitrary integer as indicated in this diagram. Now, the technique that we will follow to design the complete filter bank is, let us look at H0M. This is the real impulse response of the low pass filter, the first low pass filter, and HKN is the response of all other filters, where K varies from 0 to capital M minus 1. We will take this filter H0N is the mother filter, right? And from this mother filter, we will try to design all other filters with this equation, where Hkn will be H0n e to the power j 2 pi kn divided by m. and we can replace e to the power minus j2 pi divided by m, capital M, by a factor which is wm, w subscript m, right? And we can modify this relation of hkn as h naught n w subscript m minus to the power minus kn, where k varies from 0 to capital M minus 1. Thus, hkz, if you take the z transform now of this relationship, you will see that it is given by sigma n going from minus infinity to infinity, hkn z to the power minus n, and we can replace hkn with h naught n, and we can take this minus n outside for because minus n is here also. So we will say that h naught n z w subscript capital M to the power k and whole to the power minus n, right? So this is a simple mathematical manipulation that we can easily do here. The variation of k remains the same from 0 to capital M minus 1. The idea is that we will take the mother filter, we will design the mother filter, and we will take it as a prototype, and all other filters will be designed based on this mother filter. After multiplying it by a factor which is a modulation factor, we will see that what is the modulation factor. Actually, W is the modulation factor. We will reach to that point, right? Now, so hkz will be equal to h naught, and this is the same equation that we will get after taking the z transform. After taking the z transform, hkz will be equal to h naught z of w subscript capital M k. Now the corresponding frequency response will be given by, you have to replace z with e to the power j omega to understand the frequency response of this filter, or this complete filter bank rather. H subscript k of e to the power j omega will be given by h naught, which is the mother filter. And if you just solve this factor here, you will get that e to the power j omega minus 2 pi k by m. Right? If you replace the value of w, the value of w I have already explained, e to the power minus j2 pi by m. Thus the frequency, and if we plot the frequency response of all other filters, see what we have tried to do is that we have taken the mother filter, and we are designing all other filters from this mother filter h naught, and we have already seen what are the characteristics of h naught. And now, since we have got the formula for all other filters, thus the frequency response of hkz is obtained by shifting the response of h naught z, because you see here the response of h naught z will be shifted by, this is the phase term, and the phase term is shifted by 2 pi k by capital M. Let us look at the diagram. So this was the frequency response of h naught, and now this is the frequency response of h1, this is the frequency response of h2, and this is the frequency response of h of capital M minus 1. These are centered at 2 pi by m, 4 pi by m, and 2 pi into capital M minus 1 divided by m. So if you look at the spectra of all the filters, they are uniformly, the distribution of the frequencies spectra is completely uniform. So that's why this is a class of uniform digital filters we are talking about. Now the question is that how to design these filters using after taking the DFT. We will take the DFT as the filter bank, and we will try to use the concept of discrete Fourier transform to design the analysis filter bank, particularly for the uniform digital filter bank. Right. Now let us look at what is the DFT as filter. What do you mean by DFT as filter bank? The DFT matrix, we all know that is an M cross M matrix. I am taking here the factor, the length of the DFT as capital M. So that matrix will be capital M into M, such that W of M is equal to omega, this is small omega, omega subscript capital M Kn. And where Wm raised to the power Kn is different, but Wm will be defined by e to the power minus j2 pi divided by m. We have already defined this factor, where capital M is the length of the DFT. Now, if you take the frequency domain samples given by x capital Xk, we all know that these are given by these are the time domain samples into omega subscript m to the power Kn, where n goes from 0 to capital M minus 1. This is the standard DFT formula. Now, if we have to get the time domain samples out of this after the taking the DFT, then time domain samples will be given by with this formula. Here we have to scale with a factor 1 by m. Then k going from 0 to capital M minus 1. K is an index for the frequency domain samples. Xk and minus sign will come here. Omega subscript capital M minus Kn. And this is basically the inverse discrete Fourier transform. And the entry in the kth row and the nth column in DFT matrix is, these are the e to the power minus j2 pi Kn divided by capital M raised to this whole term is the raised to the power. So these are the entries of the DFT matrix, and we can write it in the vector notation as capital X, which is the frequency domain samples in the frequency domain samples, and W subscript capital M is the DFT matrix, and X vector is the time domain samples. Now let us try to understand what we are doing here using capital M equal to 2, and let's try to exemplify the DFT as a DFT matrix using capital M is equal to 2. Now as I said, the entry in the kth row and the nth column is given by e to the power minus j2 pi Kn divided by m, and m I have taken to be 2. Now the first entry will be, because what are the indices that will vary? The indices, the index k will vary and index n will vary. K will go from 0 to 1 because capital M is 2 only, so it will go from 0 to 1, and small n will go from 0 to 1 again. Now the first entry will be k0 n0, and this is the factor. The second entry is k0 n1. These two entries are for the first row. The second row entries will be k1 and n0 and k1 and n as 1. And if you solve it, you will get the entries of the DFT matrix W2 as 1 1 1 and minus 1. Now you take if you look at the row 1, if you express the row 1 in terms of the Z transform, then you will see that it will be, these are basically the coefficients for the low pass filter. 1 and 1 are the coefficients for the low pass filter, and this is the transfer function that you will get for the low pass filter, 1 plus Z to the power minus 1. And if you look at the second row, you will see that the coefficients are 1 and minus 1. These coefficients correspond to a high pass filter, and the transfer function is 1 minus Z to the power minus 1. Right. So if you observe the rows of W2 matrix, row 1 contains coefficients of a low pass filter and row 2 contains coefficients of a high pass filter. Now it is very evident if you look at this example. Now it is evident from this example that DFT is doing something for us in terms of filtering, right? So if you look at the row 1, it is basically doing the low pass filtering. If you look at row 2, it is basically doing high pass filtering, right? And that too when we have taken capital M to be equal to 2. So that means this gives us an intuitive idea that DFT can be, the rows of the DFT can be used as filters in a filter bank, right? Where the row one will correspond to a low pass filter, the other rows will correspond to either band pass filter or high pass filter. This clearly gives us an idea that DFT can be used as a filter bank. Hence, we can interpret that DFT is a filter bank basically. Now, let us go further and consider the sequence xn from which we generate capital M sequences. So Si are the sequences that we will generate, where I goes from 0 to capital M minus 1 by passing xn through a delay line. Now, xn is the input signal. We will pass xn through a delay line, right? How many these delays? The first uh, first sequence S0n will be directly without any delay. Second sequence S1n will be with a delay 1, and so on. Now, if you do the W star here, right, and by using this formula, and you will get the subband signals x0n, x1n, x2n up to xm minus 1. What you are trying to do is that you are trying to design analysis filters using DFT as a matrix, right? Using DFT matrix. Now, Xn is the full band signal that you are applying to the input of the DFT, and these are the sequences that you will generate, and these sequences are actually the delayed version of the input signal. Sin will be equal to x of n minus I. These are the delayed version of the input sequence only, and these are fed to the W star, which is the DFT matrix only, right? And you will get the subband signal by this formula. Now xkn are the subband signal going from 0, k going from 0 to capital M minus 1. Sigma, this is sigma, where I goes from 0 to capital M minus 1, because there will be total number of M subband signals going from this index goes from 0 to capital M minus 1. SIN, these are the input sequences. These will be multiplied with WM. This minus sign comes because we are taking the conjugate here. Earlier, if you see here, this is not minus, xk is given by, what we are trying to do here is that we are trying to get the the sequence after doing the DFT. Since we are doing the conjugate here, this is W of kn by m. Here we are doing the conjugate, so therefore it will be minus sign will come, negative sign, because we take the W conjugate. This is like, if you see this formula, this is just like the IDFT, because minus sign actually corresponds here. This minus sign is for the IDFT, but this formula is similar to IDFT, but without the scaling factor 1 over capital M. So there is no scaling factor, but in the case of IDFT, there is a scaling factor 1 by M, right? And since we are taking the W conjugate, right, W conjugate will give us the minus sign here. Okay, and this is the formula to get the, this is how we will get the subband signal. This formula will help us to get the subband signals, and this DFT matrix, we will be using it as a filter bank. We have already seen that it can be used as a filter bank. Now, in this equation, if we take the Z transform, after taking the Z transform of equation 1, so this is the equation 1 I'm calling, and if you take the Z transform, this will be given by xkz, I going from 0 to capital M minus 1, siz, and this factor will be there. But we know that what is siz? Sin is x of n minus I, and if you take the Z transform, this will be equal to siz, this will be equal to siz will be equal to xz, z to the power minus I. This corresponds to the delay in the corresponding sequence. because sin is equal to x of n minus I. If you take the z transform, siz will be equal to z to the power minus I of xz. Now, if you substitute the value of siz here, you will see that it is z to the power minus I xz and w of minus ki. If you do little manipulation, that you take this I, the exponent value I common, minus I out, you will see that it will be inside the operator will be z w m k and the whole exponent minus I of xz. Right now, if now this is basically xkz, this is basically hkz, because xkz we will be getting from the, what is xkz are now let us look at the starting. Okay, let's look. Okay, this is the analysis filter. This is xn. This is the input signal. If you take the z transform, this will be xz. Now these are the subband signal. This can be represented by xkz if you take the z transform. So xkz corresponds to the subband signals. Xz corresponds to the full band signal. So we can say that here, we can say that xkz, which is basically the subband signals in the frequency domain, will be given by the filter response after passing through the filter band, and xz is the full band signal. This is this corresponds to subband signals, because k is an index that will vary from 0 to capital M minus 1. Hkz corresponds to the transfer function of the different filters. Xz is the full band input signal. Right now, hkz, if you compare this equation with this equation, hkz you can equate it to h naught z, h naught of z wm to the power k. Right, and we will see that h naught z will be given by we have already seen this thing yeah, it is here, because this hkz is basically the filter response of all other filters in the filter bank, where h naught is the filter response, the low power, the low pass filter response. Right, the starting filter. And the strategy, I told you that strategy we will be using to design the digital filter bank is that we will start from the mother filter and we will get all other filters from the mother filter. Right, if you put hkz, now hkz we know is equal to h naught of z wmk, and this h naught z will be given by 1 plus z to the power minus 1 z to the power minus 2, where h naught z is the mother filter. This is the low pass filter that we will design. After designing this, you can obtain hkz. Now, rest of the filters, hkz means rest of the filters. Rest of the filters can be obtained by changing the parameters of the mother filter. Now, what is the parameter? This is h naught. This corresponds to h naught z. The parameter in the transfer function of the mother filter is wmk. Now, wmk we will call as the modulation factor. By having a modulation factor, we can construct rest of the filters from the mother filter. You have to just multiply the modulation factor with the response of the mother filter, and you will be able to design all other filters. Now, it shows us the following. The DFT system is like a filter bank with analysis filter HKZ, and we can verify that H naught Z, which is the magnitude response of the mother filter, will be given by sine of modulus sine of m omega by 2 divided by sine of omega by 2. And the magnitude, the frequency response of all other filters can be expressed in terms of the mother filter by h naught of e to the power j omega minus 2 pi k by m. We have already seen this formula. Now, if you solve these equations here, right, you will be able to achieve this this frequency response for all of the rest, all other filters. Now the point is that because what we have done till now is that we have been able to design the filter bank using DFT matrix, and we saw that DFT matrix can be used as a filter bank. We applied the filtering through the DFT matrix. The idea is that we will design a filter which is the mother filter H naught, and all other filters will be derived from the mother filter by after multiplying it with the modulation factor WMK. Now, if we look at the computational capacity of an M-band uniform DFT filter, the direct implementation and the DFT implementation, and you see that an M-band uniform DFT analysis filter bank based on an N-tap prototype low-pass filter. If you take a low-pass filter, which is an N-tap, basically the number of coefficients are N, then of the base of the prototype low-pass filter, and if you design the DFT filter bank, analysis filter bank from there, then the number of multiplications required are m by 2 log to the base 2 m plus n, right? On the other hand, if you do not use a DFT analysis filter bank and you use a direct implementation like this, then you will require n into a capital N into m multipliers. So you clearly see here the complexity of the filter bank using a DFT matrix is reduced, and the complexity of the DFT as a filter bank is given by m by 2 log to the base 2 m plus n, whereas the direct implementation it is n into capital N. So clearly it shows that we can use DFT matrix as a filter bank to design the analysis filters. Thank you.